The Sun's outer atmosphere is a million-degree mystery. While the Sun's visible surface, the photosphere, sizzles at about 5,500 degrees Celsius or approximately 10,000 degrees Fahrenheit. This is actually one of the cooler layers of the Sun. This seems counterintuitive, doesn't it? Imagine stepping away from a campfire and feeling the air get hotter instead of cooler. That's precisely the perplexing phenomenon observed with our Sun. To fully grasp this, we need to understand the Sun's internal structure. Deep within its heart lies the core, a superheated powerhouse where nuclear fusion reigns supreme. Here, temperatures soar to an astonishing 15 million degrees Celsius, 27 million degrees Fahrenheit, and the density is immense, about 150 times that of liquid water. It's in this extreme environment that hydrogen atoms fuse to form helium, releasing the incredible energy that powers our star. Moving outward from the core, we encounter the radiative zone, extending to about 70% of the Sun's radius. In this region, energy is transported primarily by photons, which scatter countless times off dense plasma particles, taking roughly 1 million years to traverse this zone. As energy radiates outward, the temperature gradually decreases, dropping from approximately 7 million to 2 million Kelvin. Next is the convection zone, the outermost layer of the Sun's interior, stretching from about 200,000 kilometers deep right up to the visible surface. Here, the plasma is cooler and less dense, allowing for energy transfer through convection. Hot plasma rises in colossal bubbles, cools as it approaches the surface, and then sinks again, creating a continuous, boiling motion. These convective currents are visible on the photosphere as granulation and supergranulation. The temperature at the base of the convection zone is around 2 million degrees Celsius, and it continues to drop as the plasma rises. So, by the time we reach the photosphere, the temperature has fallen significantly from the Sun's core. The photosphere itself is a relatively thin layer, about 100 to 400 kilometers thick, and its temperature ranges from roughly 4,400 Kelvin at its top to 6,600 Kelvin near its bottom. This is the layer from which most of the Sun's visible light is radiated, making it the surface we perceive. However, the paradox truly begins as we move above the photosphere into the Sun's atmosphere. The layer immediately above the photosphere is the chromosphere, where temperatures actually start to climb again, reaching around 20,000 Kelvin at its upper boundary. But the most dramatic temperature increase occurs in the corona, the Sun's ethereal outer atmosphere. Here, temperatures can skyrocket to an astounding 1 million to 2 million Kelvin, and even up to 20 million Kelvin in some active regions, and occasionally as high as 40 million degrees Celsius during solar flares. This means the corona is hundreds, if not thousands, of times hotter than the photosphere beneath it. This inverse temperature gradient, where the outer atmosphere is vastly hotter than the surface, is known as the coronal heating problem, and it has puzzled solar physicists for decades. It defies our everyday experience of heat dissipation, where temperature typically decreases with distance from a heat source. The energy generated in the Sun's core certainly flows outward, but the second law of thermodynamics dictates that heat cannot spontaneously flow from a cooler region, the photosphere, to a hotter one, the corona. Therefore, some other form of energy, not just direct heat transfer, must be at play to superheat the corona. Scientists have proposed several theories to explain this paradoxical heating. One prominent idea involves magnetic reconnection, a process where magnetic field lines break and reconfigure, releasing immense amounts of stored magnetic energy. This released energy can then be converted into thermal and kinetic energy, heating the plasma and accelerating particles. Magnetic reconnection is known to occur throughout the solar atmosphere, from the photosphere to the corona, and is particularly associated with explosive events like solar flares and coronal mass ejections. Another leading theory focuses on waves, particularly alphane waves. These are a type of plasma wave where ions oscillate in response to tension on magnetic field lines. Alphane waves are thought to be generated in the turbulent convection zone and photosphere, then propagate upward into the corona, carrying energy with them. As these waves travel through the increasingly thin plasma of the corona, they can dissipate their energy, transferring it to the coronal gas and heating it to millions of degrees. Observations from spacecraft like Hinode and the Solar Dynamics Observatory have provided evidence for the presence of highly energetic alphane waves in the solar atmosphere, carrying sufficient energy to heat the corona. Recent research, for example, has explored the role of kinetic alphane waves in this process, investigating how they transfer energy to plasma particles. The Parker Solar Probe, a NASA mission designed to touch the sun, is providing unprecedented data to help unravel this mystery. By directly sampling the corona, the probe is offering crucial insights into the mechanisms at play. Early findings from the Parker Solar Probe have, for instance, investigated the role of switchbacks, S-shaped bends in the sun's magnetic field, as a potential heating source. While these switchbacks are common in the solar wind near the sun, their absence within the corona itself suggests they may not be the direct cause of coronal heating, although the mechanisms that form them could still contribute. The probe is also exploring the unexpected presence of dust grains close to the sun, which may influence how plasma waves transport and dissipate energy, offering a new avenue of research into coronal heating. The coronal heating problem is a testament to the complex and dynamic nature of our sun. It's a powerful reminder that even with our closest star, there are still fundamental questions to answer, pushing the boundaries of our understanding of astrophysical processes. The resolution of this paradox will not only deepen our knowledge of the sun, but also provide crucial insights into the behavior of other stars across the universe and improve our ability to predict space weather events that can impact Earth. The sun, a colossal sphere of superheated gas and plasma, doesn't possess a solid surface in the way Earth does. Instead, what we perceive as its surface is a dynamic and luminous layer called the photosphere. The name itself, derived from ancient Greek, means sphere of light, a fitting description for the region from which most of the sun's visible and infrared energy radiates into space. This incandescent surface is surprisingly thin, spanning a mere 100 to 400 kilometers in depth. To put that into perspective, it's an incredibly shallow shell compared to the sun's immense radius of nearly 700,000 kilometers. Despite its thinness, the photosphere is the origin of almost all the light we receive from our star, acting as the boundary where photons, the carriers of light energy, finally escape the sun's interior without being constantly absorbed and re-emitted. The temperature within the photosphere is far from uniform. It ranges from about 6,400 to 6,600 Kelvin, approximately 6,127 to 6,327 degrees Celsius, or 11,060 to 11,390 degrees Fahrenheit, at its base, gradually decreasing to around 4,400 Kelvin, about 4,127 degrees Celsius, or 7,427 degrees Fahrenheit, at its upper boundary, where it transitions into the chromosphere. This temperature gradient is crucial to understanding a phenomenon known as limb darkening. When we observe the sun, its center appears brighter than its edges, or limb. This isn't an optical illusion. Rather, it's because when we look at the center of the solar disk, we're peering into deeper, hotter, and therefore brighter regions of the photosphere. Conversely, at the limb, our line of sight passes through the upper, cooler, and dimmer layers of the photosphere, resulting in the observed darkening. The photosphere is primarily composed of hydrogen, about 74.5% by atomic mass, and helium, about 23.5%, with a small percentage of heavier elements like oxygen, carbon, and nitrogen. Although it's a gaseous layer, its density is about 1/1000th that of Earth's atmosphere at sea level, making it much more opaque than one might expect due to the strong absorption of light by hydrogen ions. If you could hypothetically stand on the photosphere and somehow withstand the extreme temperatures and radiation, you'd find yourself in a superheated, bubbling soup of plasma, not a solid surface. One of the most striking features of the photosphere, readily observable with specialized telescopes, is its mottled, granular appearance, often likened to boiling oatmeal or grains of rice. This granulation is direct evidence of convection currents at work beneath the sun's surface. Hot blobs of plasma, each roughly 1,000 kilometers, about 600 miles, in diameter, rise from the hotter convective zone below, spread out across the photosphere, cool, and then sink back down in the darker lanes between the granules, only to be replaced by new, rising cells. These individual granules are ephemeral, typically lasting only a few minutes before dissipating and reforming in a constant, churning pattern. The vertical convection velocity averages about 2 kilometers per second, sometimes reaching supersonic speeds of up to 7 kilometers per second, generating acoustic waves in the photosphere. Beyond these individual granules, there are even larger, harder to observe structures called supergranules. These colossal cells can span up to 30,000 kilometers, around 19,000 miles, in diameter and have lifespans of approximately 24 hours. Supergranules play a vital role in sweeping magnetic fields to their edges, where jets and eruptions can occur. Another prominent feature of the photosphere, and perhaps the most easily recognizable, are sunspots. These appear as dark patches on the sun's visible surface because they are cooler than their surroundings, with temperatures as low as 3,000 degrees Celsius, 5,400 degrees Fahrenheit. Sunspots are indicators of intensely concentrated magnetic fields that break through the photosphere, inhibiting the upward flow of hot plasma from the convection zone below and thus causing the localized cooling. Observing the movement of sunspots across the solar disk was instrumental in revealing that the sun rotates on its axis, and that this rotation is differential, meaning the equatorial regions rotate faster, approximately every 24 days, than the polar regions, over 30 days. Associated with sunspots, and often found near the limb of the sun, are faculae. These are bright areas, best seen at the limb where the overall photospheric intensity is reduced by limb darkening. Like sunspots, faculae are also associated with strong magnetic fields, which in this case channel excess heat to the surface, making these regions appear brighter. The photosphere is also where almost all features of the sun's visible light spectrum originate, including the dark Fraunhofer lines. These absorption lines, first described in the early 19th century, provide crucial information about the chemical composition and physical conditions of the solar atmosphere. The magnetic fields in the photosphere are not only responsible for sunspots and faculae, but are also a fundamental driver of solar activity. These fields loop through the solar atmosphere and interior, forming a complex web of structures that extend into the chromosphere and corona. Scientists measure these magnetic fields in the photosphere and then use mathematical models to map their configurations into the outer layers of the sun, which helps in understanding and predicting space weather events. The behavior of these photospheric magnetic fields is closely coupled to the layers above, influencing the dynamics and heating of the chromosphere and corona. Understanding the photosphere, therefore, is not just about observing the sun's visible facade. It's about delving into the intricate interplay of convection, magnetism, and radiation that defines our star and, by extension, other stars throughout the cosmos. Beyond the photosphere, where the temperature is a mere 5,800 Kelvin, lies one of the sun's most captivating and perplexing features, the corona, its outermost atmospheric layer. This ethereal, pearly white halo, best observed during a total solar eclipse, presents a profound enigma to solar physicists. Why? Because, defying all intuition, the corona is dramatically hotter than the layers beneath it, reaching astonishing temperatures of 1 to 2 million Kelvin, and even up to 20 million Kelvin in active regions. This dramatic temperature inversion, where heat flows from a cooler region to a much hotter one, is known as the coronal heating problem, a mystery that has baffled scientists for decades. The sheer scale of this temperature difference is staggering. Imagine moving away from a campfire, only to find the air getting progressively hotter as you distance yourself from the flames. This is precisely the paradox presented by the sun's corona. The second law of thermodynamics dictates that heat cannot spontaneously flow from a colder body to a hotter one. Therefore, some non-thermal process must be at play, transporting energy from the sun's interior and converting it into heat within the corona itself. For much of history, the corona remained an elusive spectacle, only revealing itself during the fleeting moments of a total solar eclipse. Early observations in the 19th century, particularly during an 1869 eclipse, unveiled peculiar spectral lines that didn't correspond to any known elements on Earth. This led some to hypothesize the existence of a new element, coronium. It wasn't until the 1940s that scientists correctly interpreted these spectral features as highly ionized atoms, primarily iron, Fe(X)Iv, or Fe13+, indicating temperatures in the millions of degrees. This discovery formally established the coronal heating problem. The corona itself is a tenuous plasma, far less dense than the photosphere below. Its density is roughly 10 million times lower than the sun's surface. This low density is why the corona is so faint in visible light, making it challenging to observe outside of eclipses. However, in ultraviolet, UV, and X-ray wavelengths, the corona shines brightly, allowing for continuous observation by space-based instruments. The solar magnetic field permeates the entire corona, profoundly influencing its structure and dynamics. Charged particles within this plasma are compelled to spiral along magnetic field lines, shaping the corona into intricate loops, streamers, and plumes. The leading theories attempting to solve the coronal heating problem generally fall into two main categories: wave heating and magnetic reconnection, often linked to nanoflares. Both mechanisms propose that energy generated in the sun's convection zone is transported upwards and then dissipated in the corona as heat. Wave heating theories suggest that various types of waves, generated by the turbulent motions of the photosphere, carry energy into the corona. One prominent candidate is Alfvén waves, a type of plasma wave where ions oscillate in response to magnetic field line tension. These waves were theoretically predicted by Hannes Alfvén in 1942 and have since been observed in the solar corona and solar wind. While magnetoacoustic waves struggle to carry sufficient energy through the chromosphere to the corona due to reflection and low pressure, Alfvén waves are more efficient at penetrating the upper atmosphere. However, a challenge for wave heating theories has been explaining how these waves dissipate their energy rapidly enough once they reach the corona to account for the observed temperatures. Recent research, particularly with observations from missions like Hinode, the Parker Solar Probe, and Solar Orbiter, has provided stronger evidence for the role of Alfvén waves. Studies have shown that highly energetic Alfvén waves, combined with energetic spicules, jet-like phenomena extending from the chromosphere, could potentially provide enough energy to heat the corona to its million Kelvin temperatures. The Daniel K. Inouye Solar Telescope has even directly observed small-scale torsional Alfvén waves twisting through the corona, further validating their potential role. The other leading contender is magnetic reconnection, often associated with nanoflares. This theory, significantly developed by Eugene Parker in 1988, proposes that the braiding and tangling of magnetic field lines in the corona, driven by photospheric motions, store magnetic energy. When these stressed magnetic field lines cross and reconnect, They explosively release this stored energy, converting it into heat and kinetic energy. Nanoflares are essentially miniature versions of solar flares, much smaller and more frequent, occurring ubiquitously across the sun's surface. While individual nanoflares are difficult to observe directly due to their low X-ray energies, simulations predict they produce faint, hot plasma at around 10 million Kelvin. The cumulative effect of millions of these tiny, impulsive heating events happening every second could provide the continuous energy input needed to maintain the corona's extreme temperatures. Observational evidence for superhot plasma, indicative of nanoflares, has been presented by missions like NASA's Eunice sounding rocket. The presence of braided substructured loops, which closely match twisted magnetic field lines, further supports the occurrence of magnetic reconnection in coronal loops. It's important to note that the coronal heating problem is likely not a single solution mystery. It's plausible that both wave heating and magnetic reconnection contribute to varying degrees, depending on the specific region of the corona. Some research even suggests that magnetic reconnection can generate waves, creating a complex interplay between the two mechanisms. The problem is further complicated by the fact that the corona is not uniform. It consists of active regions, quiet sun regions, and coronal holes, each with potentially different heating mechanisms at play. Active regions, for instance, are associated with strong magnetic fields and sunspots, and often exhibit higher temperatures. The quest to definitively solve the coronal heating problem continues to drive solar physics research. Missions like the Parker Solar Probe and Solar Orbiter are venturing closer to the sun than ever before, providing unprecedented data from within the corona itself. These observations are crucial for testing and refining existing theories and for uncovering new clues about the intricate processes that make our star's outer atmosphere a million-degree enigma. Understanding coronal heating is not just about comprehending our sun. It's about unraveling fundamental processes of plasma physics and magnetic energy dissipation that are relevant to stars and other astrophysical phenomena throughout the universe. The mystery of the sun's scorching corona, often referred to as the coronal heating problem, has puzzled scientists for decades. It defies conventional understanding, as the corona is hundreds of times hotter than the solar surface, despite being farther from the sun's core, where nuclear fusion generates heat. The photosphere, the visible surface of the sun, is a relatively cool 6,000 Kelvin, about 10,000 degrees Fahrenheit, while the corona blazes at millions of degrees Kelvin. This temperature inversion suggests that an unknown mechanism is at play, transferring energy to the corona and heating it to such extreme levels. Scientists have proposed several theories to explain this phenomenon, with two main candidates emerging as the most likely: wave heating and magnetic reconnection, often involving what are known as nanoflares. The wave heating theory, first suggested in 1949, posits that waves carry energy from the sun's interior, specifically the churning plasma of the photosphere, into the chromosphere and corona. As these waves propagate into the less dense outer atmosphere, their amplitude grows, transforming into shock waves that dissipate their energy as heat. The magnetic reconnection theory, on the other hand, focuses on the solar magnetic field. The sun's turbulent surface generates complex magnetic fields that extend into the corona. When these tangled magnetic field lines break and reconnect, they explosively release magnetic energy, converting it into thermal energy and heating the plasma. These events can manifest as nanoflares, tiny explosions that are like miniature versions of solar flares, each packing the energy of a 10-megaton hydrogen bomb. While individually small, a continuous barrage of these nanoflares across the sun's surface could collectively provide the immense energy needed to heat the corona. To unravel this enduring mystery, NASA and ESA have launched ambitious missions to directly study the sun's corona. The Parker Solar Probe, PSP, launched in 2018, is a landmark mission designed to touch the Sun by flying directly through its corona. This daring spacecraft is equipped with instruments to measure the density, temperature, and flow of the coronal plasma, as well as electric and magnetic fields, providing unprecedented in-situ observations. By venturing within 3.9 million miles, 6.1 million kilometers, of the Sun's surface, Parker Solar Probe is sampling just heated particles, removing the uncertainties that arise from observing from Earth, which is 93 million miles away. The probe's heat shield, made of a carbon composite foam, allows it to withstand temperatures up to 1,400 degrees Celsius, 2,500 degrees Fahrenheit, while the spacecraft itself remains protected. One of Parker Solar Probe's key objectives is to test the leading theories of coronal heating. For instance, it has investigated switchbacks, S-shaped bends in the Sun's magnetic field that were once thought to directly heat the corona. However, data from the probe's numerous passes through the corona revealed that while switchbacks are common in the solar wind near the Sun, they are largely absent inside the corona, ruling them out as a direct heating mechanism within that region. Another crucial mission is the ESA/NASA Solar Orbiter, launched in 2020. Solar Orbiter performs both remote sensing, using cameras to observe the Sun and its atmosphere in different wavelengths, and in-situ measurements, flying through regions to gather data on particles and magnetic fields. This dual approach allows scientists to connect large-scale phenomena with the detailed microphysical processes happening in the plasma. A significant breakthrough came from a coordinated effort between Solar Orbiter and Parker Solar Probe in June 2022. Through careful orbital maneuvers, Solar Orbiter's Métis instrument, a coronagraph, was able to remotely observe the corona, while Parker Solar Probe simultaneously took in-situ measurements of the same plasma. This allowed for the first ever combined observational and in-situ estimate of the coronal heating rate. The data strongly supported the theory that turbulence in the solar atmosphere plays a significant role in heating the corona. This turbulence transfers energy from larger to smaller scales, eventually converting it into heat, similar to how stirring a cup of coffee dissipates energy. Further observations by Solar Orbiter's Extreme Ultraviolet Imager, EUI, have also revealed small-scale, fast-moving magnetic waves whirling on the Sun's surface. Calculations suggest these fast-oscillating waves produce enough energy to potentially explain the coronal heating. Beyond these two prominent missions, other spacecraft like SOHO, Solar and Heliospheric Observatory, Yoko, Hinode, and TRACE, Transition Region and Coronal Explorer, have provided invaluable data, imaging the Sun's soft X-ray and ultraviolet emissions and revealing the highly structured and dynamic nature of the corona. Upcoming missions and continued analysis of data from Parker Solar Probe and Solar Orbiter promise to bring us even closer to solving this long-standing astrophysical puzzle. The insights gained from understanding coronal heating extend beyond our Sun, offering a window into fundamental processes of plasma physics and magnetic energy dissipation relevant to stars and other astrophysical phenomena throughout the universe. The corona, as we've explored, is a superheated, enigmatic region. But it doesn't just sit there. It constantly expands, shedding a continuous stream of charged particles into space. This is the solar wind, a cosmic breeze that permeates our entire solar system and beyond, acting as an extension of the Sun's magnetic field. The solar wind is primarily composed of ionized hydrogen, protons and electrons, and fully ionized helium, alpha particles, with trace amounts of heavier elements like carbon, nitrogen, oxygen, and iron. These particles are ripped apart by the extreme temperatures of the corona, forming a plasma. This plasma is so hot that the Sun's gravity cannot contain it, leading to its outward expansion. There are two main types of solar wind, fast and slow. The fast solar wind, traveling at speeds between 500 and 800 kilometers per second, approximately 1.1 to 1.8 million miles per hour, primarily originates from coronal holes, regions of lower density and temperature in the corona where magnetic field lines are open and extend outward into space. These coronal holes are often found near the sun's poles, especially during periods of solar minimum. The slow solar wind, on the other hand, moves at a more leisurely pace of about 200 to 400 kilometers per second, approximately 450,000 to 900,000 miles per hour, and is thought to emanate from coronal streamers and other solar features typically found around the sun's equator. While the fast solar wind is relatively consistent in its properties, the slow solar wind is much more variable in terms of speed, density, and temperature. The precise mechanisms driving the acceleration of the solar wind, particularly the fast wind, have been a long-standing puzzle in astrophysics. For decades, scientists have debated whether magnetic reconnection or acceleration by plasma or alphane waves is the primary cause. However, recent observations from NASA's Parker Solar Probe have provided crucial insights. The probe has detected streams of high-energy particles within coronal holes that match supergranulation flows, suggesting these are the source regions for the fast solar wind. Furthermore, Parker Solar Probe's instruments have recorded magnetic field switchbacks, sudden reversals in the direction of the magnetic field carried by the solar wind, which appear to be associated with the regions where the solar wind is generated. These switchbacks, along with the presence of extremely high-energy particles traveling 10 to 100 times faster than the solar wind average, strongly suggest that magnetic reconnection plays a significant role in accelerating the wind. This process, where magnetic field lines rapidly reconfigure, transfers magnetic energy to particles, heating the plasma and providing enough energy for them to escape the sun's gravity. As the sun rotates, its magnetic field lines are dragged outward by the solar wind, forming a complex, spiral pattern known as the Parker spiral. This interplanetary magnetic field, embedded within the solar wind plasma, extends far beyond the orbits of the planets, creating a vast bubble around the sun called the heliosphere. The heliosphere is the region where the solar wind dominates the interstellar medium. The solar wind, though invisible, has profound effects throughout the solar system. When it encounters a planet with a magnetic field, like Earth, it interacts with the planet's magnetosphere, a protective magnetic shield. Most of the solar wind is deflected around Earth's magnetosphere, but some charged particles can penetrate and travel along Earth's magnetic field lines towards the poles. The interaction of these particles with gases in Earth's upper atmosphere excites the atoms, causing them to emit light and create the spectacular auroras, the aurora borealis, northern lights, and aurora australis, southern lights. Beyond the beautiful auroras, the solar wind can also trigger geomagnetic storms, which are disturbances in Earth's magnetosphere. These storms can have significant impacts on our technology, potentially disrupting satellite communications, GPS signals, and even power grids. They can also pose a threat to astronauts in space. The intensity of these effects varies with the solar cycle, as the properties of the solar wind, such as its density and speed, change during periods of high and low solar activity. The solar wind's influence isn't limited to Earth. It shapes the magnetospheres of other planets, and its interaction with bodies lacking strong magnetic fields, like Mars and its moons Phobos and Deimos, can lead to complex electrical environments. Understanding the solar wind is crucial for comprehending the space environment, predicting space weather, and ensuring the safety of our technological infrastructure and future space missions. Missions like the Parker Solar Probe, which has already broken records for speed and closeness to the sun, continue to provide unprecedented data, helping scientists unravel the remaining mysteries of our star's powerful outflow. Future missions, such as ESA's Solar Wind Magnetosphere Link Explorer, SMILE, will further investigate how the solar wind interacts with Earth's magnetic field, aiming to improve space weather forecasting. The potential for harnessing the solar wind for spacecraft propulsion through concepts like solar sails also represents an exciting frontier for future space exploration, offering the possibility of long-duration, fuel-efficient journeys to distant reaches of the cosmos.